Okay. Thank you, Peter, for the invitation, and thank you all for coming, despite the very nice weather outside. Just to have an idea of who you are and what brings you here. Who has some experience with reinforcement learning? Some. Okay. So the rest is more or less new, kind of general curiosity, let's say. Okay, that's good, because the aim of my talk is to make it more like conceptual rather than technical. So I apologize to the reinforcement learning experts in the room if I'm not going to surprise you with some great results. So what I want is just to introduce the framework. Reinforcement learning is really that, a framework, a way of thinking of strategic decision making and their uncertainty, this kind of problems, and hopefully try to demystify the hype, which I guess we all know all too well that is around about machine learning and reinforcement learning and deep reinforcement learning as the cure for everything, every sort of problem ever. So let's try to get away from that. I taught a course on games theory and reinforcement learning during last semester in Czech Technical University, and well, I think it's a great case study on deceptive advertising, because what the students were waiting was how to program maybe some artificial intelligence that plays in Warcraft, but my background is more from mathematics and economics, so I'm a business consultant, so I was more interested in other kinds of problems. Anyhow, I think we managed to agree, and we got a decent course out of it. Hopefully, for the next time, I will, learn from the environment and improve my course. So who am I? So, well, I work as a freelance consultant in math applications and data science stuff, whatever that means. And I'm also teaching, so as I said, on Czech Technical University and on the Economics Discovery Hub from time to time. My background is in mathematical game theory. And yeah, well, as Peter pointed out, I'm the first attendant to the first machine learning meetup, which was a very, very interesting experience. It was not in Paralelni Polis. It was in BRM lab around Beltavska. So I had to go as a foreigner who doesn't speak Czech, who didn't speak any Czech at the time, and find the room in this very, very nice Soviet era factory. Was a good experience. And well, I've tried to come ever since, as much as I can. Okay, so to the point. So, what's the reinforcement learning problem? Sorry, do you have a question? Sorry.
I have a question.
Okay, sorry. Yeah, please.
First question: what was the topic of your PhD?
Topic of my PhD was zero-sum games and mean field games. Mean field games. Mean field. Yeah. Okay. Yeah. And the second question?
That's exactly introduction to advanced reinforcement learning.
Introduction to advanced reinforcement.
What do you think in the subject?
Well, this presentation is kind of a sip of the course, so maybe that's will answer. Okay. More questions? No. That's okay. Okay. The reinforcement learning problem. So what we're interested in is the following scenario. We have an agent, which can be a computer program, an animal, a human, or something. And this agent, this someone, learns by interaction with an environment on which he lives. And this agent has a goal. It's either achieve something or maximize some reward during its lifespan on this environment. And we want to model, we want to help this agent to achieve its goal, to maximize its reward, or to achieve whatever it needs to. In some way, it's more realistic and ambitious than other types of machine learning, because you don't know what the what the level of some case is, let's say, so some training example. You try to discover it on the go. Yeah? And perhaps the best way is to use an example. This is not mine, but I would strongly recommend to visit this GitHub page. It's a great tutorial on reinforcement learning. And if you see here, so what is this? We have a small agent, which is this little circle, and he wants to achieve to reach to T. And what he's trying to do is to guess which actions, left or right, should he take in order to achieve. So this is like the general, in a nutshell, the reinforcement learning problem. Yes? There's a Chinese also. So the guy is Chinese, but then he did English tutorials as well. Yeah? Oh, no, there should be also English somewhere. Okay, so this is the setup. Yeah? So we have someone that lives in an environment, makes decisions, and gets some rewards out of it. It comes from many different ways, from many different sources actually. People from animal psychology started proposing it as started getting interested in how animals adapt their behavior through reward signals they get from the environment in the early 20th century. People from optimal control and dynamic programming also started to think about this kind of problems. There's lots of stuff. It's done in the 50s, but main ideas come from even further, so from the 18th century and so on. And in operations research and economics, you have this very often. Think, for example, the case of a car rental agency who wants to allocate vehicles that would satisfy the demand. So you have two branches of your car rental agency, and you want the people who come to your branch to always get a car, and you don't want extra cars misdistributed. So you have a state, which is the distribution of your cars in both agencies. You have an action, which is the allocation of the cars, and you have a reward, which is whether the people got satisfied when they came to your agency, meaning that when they came to visit you, they were received with the car they expected. And well, finally, in robotics, so think of the case of a mechanical arm that needs to perform some task. So there's the state, which is a configuration of the arm, the action, how it should move, its parameters, and the reward is well at the end of a certain trial period if he managed to put the piece where it should or something. Yeah. Recent reinforcement learning success stories, which we've probably all heard of. I think the first big achievement was matching human level performance in backgammon in the late 90s by Tesoro. Then there's a very nice videos in YouTube where you can see it's part of Andrew NG, the same NG from Coursera, research on how to teach a helicopter to perform acrobat maneuvers in autopilot, just by the algorithm. It was used also on Watson, on the very famous IBM stuff for the competition in Jeopardy. And more recently, and this is more where we borrow a bit from in this talk and what we did on the course. Thanks to reinforcement learning in part, so it was possible to achieve human level performance on Atari games, just getting the feed of the screen on the game. So the computer was able to match with the same structure of the network, human level skill. We'll talk about this in a second, well, towards the end of the talk. And these are what kind of perhaps with exception of acrobatic helicopter autopilot. sort of toy problems. Yeah, so you say, well, that's all very fine. You taught a computer to play Atari, so what? Yeah, but there are actually real economic implications out of this, and this is perhaps this last one. So Google bought DeepMind and then put them to work in their stuff, and using similar techniques that you use to teach a computer to play Atari. You can also teach it to manage the load in Google's data center to reduce the cooling bill by up to 40%, which is kind of significant. Yes? Yeah. So there are two phases, let's say, of reinforcement learning we'll go through. One is model-based, so by that we mean that we know a description of the environment, how the world works. And one is model-free, so we don't need to have an explicit model of the environment. And by model, I mean just a description of the dynamics and the payoff structure that happens in the place where the agent lives. I will be more concrete in a second. And the theoretical framework to think about this is Markov. When we speak of model-based reinforcement learning, it's Markov decision processes. So just quickly introduction of the fastest introduction of Markov decision process ever. So a Markov decision process is a tuple. It's a collection of states. So think of S as a finite set of states. A is a finite set of actions. And P is a state transition probability. That means this P is think of it as like a big transition matrix. If we have only one action, there's just a transition matrix, the probability from going to one state to the other. When we index it by the action, it means that conditional on the action and on the state where I am, what's the probability to go to a different state? S prime, sorry, should be here. And then there's a reward associated to the state and the action I take on it. And we'll introduce a discount factor for mathematical reasons in a moment. So let's say we have an agent that plays on this world with this state. So how is the decision problem? So you start on a state. You receive the information on which state you are now. Then you decide to take an action. To this action, there's associated a reward. And then, thanks to the state and action, you have a probability to move to a different state in the next round. Yeah. So you go from one state. So here in state S1 is your initial state. You take an action A1. You receive a reward. And then the state S2 is chosen based on a lottery, on a probability distribution that depends on both S1 and A1. And the situation is repeated. Now you start in S2. You take an action A2. These together give you a reward of R2. And then the state S3 is chosen with a lottery that depends on S2, A2, and so on. Yeah? So after we've played T times, we see in lowercase letters the realization of the history of the play. So in the beginning, I don't know where I start, but then the state 1 happens. I receive it, I move, so I know what I did. I got a reward, which I observe, and so on. And until I come to here, this state. So this is part of the, this is the observed realized history. And then when I'm here, after leaving the time t, I'm going to go to state st plus 1, which is in uppercase because this means that this is a random variable. So I know the distribution of this random variable, which depends on these two. Yeah, I know how likely is this to be anything, but I don't know exactly which one it is. Yeah. So at this point, from my point of view, on the remaining on the game, I have a stochastic random payoff coming to me that depends on future history, which is discounted by some factor gamma. And this factor gamma, what it does is that it's giving more weight to the present. So it's better to have 100 crowns today than 100 crowns tomorrow. Yeah. So if I multiply by something less than 1, I take into account this effect.
Is gamma allowed to be 1?
Gamma could be not. Yeah, gamma should not be 1 unless there's a terminal state. So otherwise the sum doesn't make sense. Sure. And payoff should be bounded. But okay. For example, we can think of this situation as a Markov decision process. So in the blue circles, you have a state, yeah? Labeled with your state is wake up, and then you have 2 actions in red. So you have action P, which is procrastinate, and action NP, which is not procrastinate. So if you take this action, so then you go to Facebook, and then in Facebook you have 2 actions, to continue and quit. So if you continue, you get a payoff of -5 because you're wasting time. If you quit, then you go to study. You could go to study with a certain probability, and you could go to Hospoda with a different probability. Yeah? And then you get different payoffs of 5 and 10 and so on. And you're making decisions all the way during your trajectory on this graph until you reach a terminal state of sleeping. Yeah? So after you spend a lot of time in Hospoda, then you have sleeping becomes an absorbing state. And there's an episode that finishes, and then the next day you wake up and you are on the same situation. You are facing the same sequential decision problem. At each point, you go to another state. You take an action that takes you to another state, and you get a payoff out of it. Yeah. So this is the stuff. And how do you take those actions actually? So that's the full point of it. So. Let's say in this case we'd like to maximize our expected future happiness in the end, so we will probably oscillate between these 2 or something. Yeah, but how can we formalize this? So at each state we allow ourselves to choose different actions with different probability, and this is what is called policies. So the policy pi is just a distribution over actions given state. So what's the probability that I do action A when I'm in state S? Yeah, for each of the available actions I have on this state, I have different probabilities of taking it. And the policy is just like a way of living, let's say, the rules the agent is going to give to himself. So what actions is he going to take on each state? And what we are interested in is in finding the policies that are best for the agent. So for each policy, we can evaluate the quality of this, the quality of it. So if we start on state S at time st, so there's a story that passed. We cannot do anything about it, but there's a future expected payoff that can be improved from state S using this policy. So let's say that this b pi of s, this is called the state value function. So this is the expected payoff conditional on using this policy at each decision point. Yeah. So there's 2 sources of randomness. There's the randomness that comes from the environment, and there's the randomness that comes from the actions. And a related function is the Q function. So the Q function counts the expected return, but of a particular action. So think of it as like a decoupled value function across actions. So if at time t, at time t you're in state S and you took action A, what is the implications of that for the future? What's the implications of that for tomorrow? If I follow this policy. So this is this, and naturally we are interested in solving this problem, and solving means 2 things. Well, solving is 1 thing, so maximize my expected reward in the future. And to solve that, I need to know first how good a policy is. So that's called the prediction problem. So given a policy, how it will perform. And this, you can imagine that you have a large number of states and actions. It's not going to be a trivial task. And the other one is the issue of control. So how am I going to improve the policy over time? Okay. And last mathematical stuff. I promise examples will come, like real examples. So the optimal value function is just the maximum, let's say, whenever it exists, of all the policies that I could take at each decision point. And the optimal state action value function is just the maximum over the policy space of Q pi of SA. Yeah, so the best I could do. Note that the maximum doesn't need to be unique, for example. That's one complication. So there's not just one optimal way of behaving. And why would we care about this? So in the end, what we want to do is to find the real optimum policy. Yeah, and finding these functions, these auxiliary value functions, helps us to get an optimal policy. And how? So suppose you have the Q function, the optimal Q function, then a policy is just a policy associated to this Q function is just giving weight 1 to all choosing all the actions that are on the maximizer of the Q function. Yeah. The reason one uses value functions in many cases, or how it was, yes. Sorry.
Previous slide. Is there a reason to 100% one action? Like, can you make some of the
Yeah, you should. Yeah, there's no reason. So if the Rmax is just 1 point, then you will just choose one optimal action. If you have many optimal actions, you can choose.
You can make like.
Yeah. Yeah, this is a mistake. No, thanks. So the reason that we use value functions is, well, one let's say historical reason is Bellman equation, and the thing is that the optimal value functions satisfy certain recurrent relations, which make it easy to find a closed form for it. So if you think of it as a fixed point operation on the space of functions, then it gives you like a recursive algorithm to find the optimal value function. Once you have the optimal value function, you can derive the policy out of it. Yeah. So this is one reason why people are interested in calculating the value functions explicitly, not the policies themselves. And then this is called value iteration. So using this recursive relation, you derive the optimal value function from which you can derive the policy. But you can actually do kind of the improvement of the policy and the discovery of the value function at the same time. So let's say you start with a policy, then you evaluate what this policy does. So you calculate the Q function. So how is this policy going to be good from the future? And then on each stage, you improve the policy a bit. So you see what this policy tells me to do. And I choose an action, and then I modify my policy. I receive a signal from the environment, which helps me to get a new policy, because on the next stage, when I see the new realization of the state and I take an action according to the policy and I see the reward, I will say how good that policy was. And then I just update and repeat this. There's just a small catch on it. So I cannot really, if I would choose at every stage the action that is better according to the policy only, then I would limit myself to very, very few actions, and I will not have the chance to explore. So what we do is that we allow the policy to be epsilon greedy, which means that I can, at each step, I will choose with a small probability an action which is not optimal, which is not on the set of optimal actions that I discovered on the Q function. Yeah, and then I tune down the randomness at every time so that eventually I will only choose optimal actions, but not on the beginning. On the beginning, I will have high probability of exploring, and this is to give time to the agent to learn all the possible combinations and see which ones are successful or not. Okay. You can decrease it exponentially, so multiply by a small weight each time. So let's say you start with, on the first stage, 100% randomly. On the next stage, so you say, you see what happened. You say, okay, so this action was good, so I will choose this one with probability 10%, and with probability 90%, I will choose whatever else. Yeah, so that I don't get stuck on just the action that I discovered. Yep. You adapt. So you change. So on the first stage, 100%. On the next stage, 90% of randomness. On the third stage, 80%.
Is it always like this, or do you adapt the epsilon according to?
You can do more complicated scheduling. Yeah. One way of learning how to behave optimally is to first learn how the model works. So I know I have a signal from the environment. When I'm in state S, I take an action, I get a reward, and I go to a different state with different probability. I can sample this. I can try to guess what's the representation of the world, and that's not so. It's kind of straightforward. So when you have the state and the action and you're discovering the reward, well, this is just a supervised learning problem, right? And learning the function that maps from states and action to the next state is just a density estimation problem. Okay, just. So it's not trivial, but it's not super complicated. So one thing we can do is like, okay, well, let's say I will just count. No, I will just run randomly my agent, and I count the number of state actions that I visit with a certain policy, let's say, and then I see, I estimate just by sampling the rewards, both the rewards and the transitions, and see where this takes me. And where this will take me to is to an approximation of the model. I will have an approximate description of the world. And then I can try to use, for example, value iteration or policy iteration to derive the optimal behavior out of it. The problem, and this is what discouraged people, I guess, from the very early 70s to when they realized that they had not enough capacity to deal with all these problems. The problem is in continuous state or action spaces, then this can become very quickly prohibitive. So it's not hopeless, but then it becomes a lot of hacking on the knowledge, explicit knowledge of the problem to see, okay, well, I know from domain knowledge that the value function should belong to this certain family, and I know the transition structure should belong to this family, so then maybe I can estimate something. So, but it becomes tricky. And what happened recently is that thanks to the computing power being so cheap comparatively, that it's possible to really tackle these problems that were kind of left out on the 50s, or just left to really government agencies with infinite budget. And now it's for everyone to try in Amazon with a few dollars. And this is Without having a description of the world, we are on the, let's say, model-free setup. Now we will assume that we have no transition structure, no reward structure, and we have no interest in getting them. Yeah? So we'll just count states and actions, see how they are performing, and then use this sort of cooling schedule, like in simulated annealing or other optimization algorithms, to reduce the amount of randomness at every time. And I will show how this works.
Just a quick question.
Sure.
With the model free, does it mean that there's no MVP?
Model free means that I will believe that there's an MDP somewhere, but I will not try to calculate it. Yeah, so I will somehow act as if there was, but I will not ask myself what is it. So one thing that you can do is to try to guess it, to try to reconstruct the model from the interaction, but this can be not a good idea. Where am I? Oops. Okay. Oh, sorry about that. Okay. So this is OpenAI, this Gym, and this is a collection of like small games on which you can try different algorithms and try to teach your computer to play with them. So the environment is given for you, and you just can quickly try. So what we are seeing now here is, I hope you can see it, because it doesn't go much bigger than that, I'm afraid. Okay, not exactly useful. But so the thing is that you are on the beginning, on the left corner. This is the start position, and you want to reach this goal. It's called frozen lake. So assume that you lost something on the other end of the lake, and then there are F's and H. F means frozen, so you can safely walk through it. And H means hole. So you go through it, you fall, you die. Yeah. So the task is to reach this box from here. And now there are different ways of approaching this problem. So this is an episodic task. So it means that at some point you die. And what you can do is to try to just. Sorry, the first, yeah, sorry.
For me, it's better. Or you can zoom in the page.
Maybe, yeah. That's a great idea. Okay, better now. Yeah. Okay, yeah. So what is this doing is just like replaying what I was. What I programmed and just sampled some of the episodes. So the one way of solve this kind of task is just say you collect the state actions reward all the time until you die, and until either you go to the in this task there's no reward, no intermediate reward. There's just a reward of 1 when you get to the end. So you collect all the state action reward vector, and you try to find the optimal combinations of states and actions that will lead to the reward in the end. How does this look on the algorithm? Oops. So you count the number of times that you are on each state and action. Then you update the queue function. So how good that action on that stage was, and whether it led to some reward on the future. And from here, from the queue functions, you derive a policy, which you will improve with a, let's say, epsilon greedy schedule. So you say on iteration k, I will use epsilon as 1 over k. So I will have a 1 over k degree of randomness. So on the beginning, I will have epsilon being 1. On the second round, my epsilon will be 1/2. So I will behave 1/2 with the best action I have found so far for that state. And with probability 1/2, I will try something new, try to improve it and get some knowledge of the environment. GD is the expected future reward from states, ST. Yeah, so according to the current policy and values.
Maybe you explain about what if the goal is not feasible?
What if you can't?
Maybe example you showed.
Uh-huh.
Happens if there is no way to start the goal.
Well, in this example, you always die. You either die or go to the end. Yeah. So yeah, there should be some timeouts to. I guess in some like some problem with there's a physical barrier maybe. You mean?
No, I mean in general, if you expect your goal to be feasible.
Yeah. Yeah, or you would put some penalization if it takes too much iterations and forget about it. Okay. So that's one thing. So you can either let's say wait until the end of each episode. You try to improve the policy up to that in the end, but that's kind of sad, no? Because what it means is that you are only learning when you die, and this is not probably a good thing. So there are actually ways of learning from the experience directly. Look, so while you are playing, you try to update your new knowledge, your new estimate of the world, and this is what's called temporal difference methods. And so the story is as follows. So you start with a random initialization of the Q function, and at each episode, so you choose an action from the policy derived from the Q function, and then take the action, then observe the reward that you get from it and the state S prime, so the state to which you arrived, and then look one step on the future using the same policy, and update the value of the Q function depending on what you would do if you would follow the same policy tomorrow. So I say, okay, so today on state S, I follow my policy, I get state A. I know that tomorrow I will go, so I observe that tomorrow I'm on state S prime. And what if I did on state S prime, what is dictated by my policy? So and then this, I will propagate it back to today's state, so to yesterday's state, yeah? So I update this knowledge by, I move in the direction where there's an improvement. So if this is positive, it means that I will increase the value of the Q function. So this action on this state is better than before. If this is negative, it's the other case until reach a terminal state. So at every point, I'm looking one step ahead and see what would happen if I would follow the same behavior. And this is almost the standard Q-learning. It's called SARSA, so state action reward, and then state action because you sample the state and you follow the action with the same policy. But you are what is called on policy. You are following all the time the same policy you have. Yeah, I will explain the difference with Q-learning in a sec. And this is a bit better because if you see here, so in 100 episodes, the average reward was kind of bad on this particular task. But if you go to Where is it? We go to this, then the performance is much better. Just get it somehow there. Yep. So what we see is that after it takes some time, but it gets a much better average reward at some point. Why? Because he's updating, he's learning at every point how the policy is behaving, and even if the policy is being updated slowly, because you need to wait until the end of an episode to change it, it's still much better than just randomly looking. And another similar method is Q-learning, as you said, and the dynamics is pretty much the same, except for one important thing. So when you update the Q function, you have some sort of wishful thinking here. So you say, okay, so in Sarsa you just add here the value of the Q function on tomorrow's state, but in Q-learning you say, okay, so the direction of improvement would be such that I will say that tomorrow, when I will be the new today, when I'm in state S prime, I would behave optimally. So I will not sample the action from my policy. I will just choose the action that is best on this state, and I will kind of respect it. No? So it's like having like a good intention from tomorrow on. Okay. And then you continue the update as before. So what it does, this is no longer on policy, because I'm not following, I don't learn how my policy is performing. I move in the direction of the best, on which the best policy is going. Yeah? So I'm trying to imitate the best policy. It doesn't make a lot of difference in this case problem, so I will not show it, but yep. So the difference is here. Yeah. So in state S prime, you choose not A prime, which is the action derived by the policy, but the action that maximizes the Q value from that state on. Yeah. So the expected payoff. So on policy learning means just like learning on the job. So I learned about the policy by just doing it, sampling experience out of it. Whereas off policy learning means shadowing someone. I'm shadowing the best policy. I'm trying to learn about how the optimal policy should look while I follow just my exploratory policy. Okay. Okay. I'll skip this part. This is all very well, but if you see, well, in reality, what these methods are doing is just keeping track of state actions. Yeah, so everything is done through the Q function, regardless of the update you are using. It's Sarsa or Q-learning, but you are still storing a huge matrix of things, and huge can be really bad. So for backgammon, we're speaking of 10 to the 20 different states. So not considering the actions available at each state. But with Go or chess, it goes just wild, yeah. So at the point where it's just not possible to store it at all. So you, from the math point of view, you have an algorithm, you have a convergence proof, and that's all solved and all very well. But in practice, it's just not tractable. Is the continuous? Sorry. It's the same. I'm not sure, to be honest. I'm not a Go player. Maybe we can ask someone later. Yeah. So what we do in those cases when either the state or actions is just too large, is to try to approximate the Q functions through some parameter vector. So try to find a compressed, in some sense, representation of those. And we can think of this parameter vector as, for instance, weights on a neural network or coefficients on some regression model. And what we're trying to do is to find among the functions that can be, let's say, described by a neural network, one that fits better the real Q function of the problem. Yeah. So that we don't have to store like all the states and actions. We can have like a recipe to generalize to get the performance of states action without keeping them all. So I'll use another example from OpenAI, this card poll. It's actually a great example to get started in reinforcement learning. So there's this request for research. So it's like a guided exercise to teach you how to use not the environment, but how to think on reinforcement learning problems. So the state is very simple. You have 4 parameters, and you have an action which is maybe you've seen this example. So you have a car with a pole on the top of it, and you want to move the car to the left or to the right, and the pole that is standing there doesn't need to bend too much, and the car doesn't need to go from some point of the screens. Yeah, so doesn't need to go all the way to the left or to the right. And when you get 200 points, meaning that the pole stays on its position and the car stays within a certain region, then you get, when you get 200 instances of those, 200 episodes correctly balanced, we consider the episode as, it's considered the episode as solved. Okay? Maybe I should show it. Where is it? So this is, oops. So this is card pole. Oh, a sec. Yeah, so I'm moving, I'm choosing the action left or right. I receive a vector of 4 parameters that describe the full state of this thing. These are the XY coordinates and the angle, and I think something else about the speed, not sure, of the angle of the pole with respect to the floor and so on. So let's say we're giving a simple update rule, which is just for each state of the car. I will give a weight of a vector of weights, and where is it? The update rule is just multiply. I start with a random initialization of the weights. I multiply it by the state of the car, and if the cross product is positive, and then I go left. If the cross product is negative, I go right. So this is my simple way of generating the policy, and I update those weights randomly. Let's say, yeah. So I'm looking for a combination of weights that give the highest score. So without any functional representation. Yeah? Yep. In this case, yes. So, but it takes some time. But okay, I will show it from the slide. So the reward that you get from the episode is just the number of instances that you correctly balanced it. So by following this simple simple update rule of the weights. Yeah, and it takes him relatively little time to find the correct combination of weights. So in most of the time, it takes him less than 10 full episodes to learn the combinations of weight, just by randomly searching. Okay, we would like to do, but well, random search in more complicated problems can be really bad. So, and it's not really functional representation. So we have a strategy that depends on one parameter. So it's just multiplying this weight vector by the state and deciding on the sign of the cross product. But that's maybe not the best we could do. So let's say we update our policy in a different way. We update the policy on the direction on which this is bigger improvement. And what happens in that case is that you can end up in regions where the function is very flat, very bad. So there's just like a marginal improvement every time, and it could take you a lot of time to reach to the point where you have a good performance. And that's because of local minimum. So random search has the advantage of being able to jump from one region to the other. And avoiding local minima. Yeah, it's just going on the look on the direction of the improvement and just follow it a bit. Yeah, and we can take in. Okay, I'll. So how we can use like more sophisticated methods, not like just random searching or hill climbing, but to do like really some educated guess. So if you look at it from the abstract, let's say, point of view, so at each state, so we have a backup, so it's like the expected value from that state. And what we would like to do is to try to treat each state and each future reward as being calculated by the current policy as an instance of a supervised learning problem, and then pass it to a neural network that will solve this supervised learning problem and update the weights of the policy accordingly to update the weights of the network that parameterizes the policy we are following in an optimal way. So our goal is to find some parameter that minimizes the, let's say, square error with respect to the real Q function of the problem. So the best optimal Q function. And how we do that is we update the parameters in the direction of the gradient as it is.
So I don't understand it. You write on all the previous episodes, basically, or?
Yeah, I'm going there. Yeah, just. So the thing is, I collect some of the of what happened. No, so I play the episode. So I have states, actions, rewards on it, and I collect it, and this will be my replay memory. So when the agent, let's say, finishes the episode and he dies, then he will have some time to think about what happened and try to update the parameter that was being used for his policy. So what you do is you choose randomly some batches of this memory you have, and then try to update the mapping that solve the supervised learning problem that to each state associates the future reward. You know how the world ended. You know how the episode was. So you know for each state what was the continuation payoff. So you update the network to fit that continuation payoff and then update it. And the reason you do it on a sample batch on a randomly selected thing is because that you want to break correlations on the data. Think, for example, that you were playing a video game and you got stuck, no, like you said, no. So you get stuck on a corner and you go nowhere, and then there's some timeout and nothing happened. No, you get a reward of 0. If you try to fit a model based on that bad experience where you got stuck, then you're not going to go anywhere. Yeah. So you will train a network that has only one point, which is being there forever. But if you just take examples of that experience, then you have an idea of how the rest of the world looks like, and hopefully that update of your parameter will help you discover new things later on. Yeah, so that's the...
So how did you discover this for the first time? Where did the alpha go?
Yeah, this is the DeepMind, the stuff. The sampling from the reflect memory. I don't know. I'm not sure. Yeah. So you take, you follow Q-learning basically, and the only difference is that you choose from this random sample here. You compute the Q-learning tileset with the previous parameter, and then you update after the new experience with a parameter that minimizes the square error. So you move in the direction of the improvement. Show in a sec. Yeah. So. So how do you find it? Well, this is the just look at this like replay function. So what you do is you follow basically Q learning. So you get a state, action, reward, then the next state, and you update the action, the weight of the action based on the action that is predicted by the model. Here, this model.predict means a model is a neural network or any function approximation method that tells you the probability of taking an action on the next state. Then you choose one of the maximizers, and then you update the value of the Q function. Then when you go, after you play the Q-learning, you fit the new value of the, you obtain the new value of the parameter by the fit method, and this is on Keras, but the interface is very similar, it's the same as scikit-learn. So if you are familiar with scikit-learn, this will ring a bell. And then state is a new update of the that you see from the dynamics, and target is the new value of the Q function. So you have a backup of the state and the future reward that you collected from that state based on the episode. You feed it on the network to try to obtain the new update on the weights, and you repeat it for some time.
So the new W, finding new W happens in the fit function.
Yeah, the finding the new it happens here. So it's some some list squares or something like that. Okay, I'm really sorry I ran out of time. This is by no means the full story, so there's a bunch of methods that I was not even planning to cover, even by my optimistic estimate of time. But I hope I would get you maybe interested on looking it up on this. We can have a chat afterwards. There are many more applications. It's just not just about game playing. There's a lot of other stuff that can be done, and generalizations perhaps to the setup with multiple agents. So similar problems of the course of dimensionality and so on that plagued Markov decision process for years are also in game theory, and it's perhaps useful to apply these new function approximation methods based on deep learning into more complicated problems. And well, thank you very much for your attention.
Okay, so we have approximately 10 to 15 minutes for questions. So any question?
Okay.
So did you need A3C in the course?
We had a very quick view of it. We didn't have time. Unfortunately, the lecture was on Mondays, and this year there were a lot of free Mondays. So
So you teach it, right?
yeah.
The course will be in the next.
The course, I didn't teach it correctly. I mean, like I just mentioned it passing by. The course will be on the next semester, and I hope we will teach it. Yeah. Sorry? Yeah. Uh-huh. You have so the state is the attributes of the passenger and the attributes of the state of the airport. So whether the flight is delayed or not, there's traffic or not, and the actions is the level of inspection that you would give to a passenger based on its attributes and the state of the airport. And well, for the reward, it's complicated. You can it's like in fraud problems. No, you know that there's some empirically some fraud rate, and you try to fit the rate, but not. It's hard to know that whether that rate makes sense or not. So it's the same stuff. Yes?
Can you tell us something more about state-of-the-art portfolio optimization? I guess this means shares, right?
Yeah. I can maybe refer you later to one student. He was working on bandit algorithms on the final project of the course for bandit algorithms, multi-arm bandits, to pick up stocks. Yeah.
What applications would you mention for algorithms that have no real understanding of the environment and the model? What kind of real world problems are you thinking that? I mean, because usually when we do this algorithm and this design, we have knowledge, the design has knowledge of the environment and the policies and so on, right? And we put these in order to save time to reach the goal faster, right? What kind of practical problems do we not do that? You have this model tree.
Yeah.
Slide, and just trying to understand where this becomes interesting after theory.
Okay. Where it becomes interesting because you don't. So you don't need to know the exact. It's kind of interesting for different reasons. No? So, if you have in video games, for example, or let's say problem of video processing, you cannot know or you cannot expect to store a big transition matrix of the video frames. So the good news is that you don't need to assume that such structure exists, so you don't need to try to even fit it, and you can still perform, let's say, reasonably well without computing explicitly the structure. It's interesting on the other direction, maybe, when you want to have more understanding of the model. Think of an economics problem, no? or some, let's say, some manufacturing problem. You would like to understand how sensitive the dynamics of the environment is to small changes. So if you can fit some transition function to it, and then you can say, okay, so this function is fairly regular. I'm not going to break the factory if I modify the action a bit. So. Yeah, whenever feasible. Yeah, but it depends on the kind of problem. I think there's like value on both directions.
And if the environment is too large, right?
Yeah, if the environment is too large, then you're yeah. So you cannot store it. Maybe for example, in some problems, maybe in robotics, the environment is more predictable. There's like a physical model of it. There's, if you're here, you will not appear there suddenly. So maybe it makes sense to elaborate more on the model. But in highly structured data, maybe not. It's not the best way. Oh, sorry. Yes.
So Google's having success behind because they've got lots of data. I was wondering, was there a minimum threshold in the examples you used before? What level of data do you need before this thing works?
I don't think that. I mean the improvement didn't came from, or this state-of-the-art results doesn't really come from having or not a lot of data. No, I mean it's like these feeds, for example, from the video games are available for everyone. It's more about computer power, I would say. So if your value function is too complicated, maybe you need to let it run for years. But I don't know if there's a minimum magic threshold that says like from if you have 10 gigabytes, forget about it. You cannot do reinforcement learning. I think no. I think there are very small problems which are still like, for example, managing call centers, or like correctly allocating the calls to the workers that have to take it. It's already complicated enough, and it's not a lot of data. Actually, that's the kind of talk I would like to go to. So I'm probably that's the kind of talk I would like to go to. So I don't know. I'm not sure. So I'm not aware. I think maybe not much, because I think maybe not much, but might be wrong. Good question. So one thing would be recommendation systems, maybe. So try to people who read something and click on it, and also so your state is like the screen you presented to the user, and you try to guess what's the future interest based on the text. I'm not sure. I think that's also kind of open question.
Can you tell us basic difference between OpenAI Gym and OpenAI Universe?
I don't know OpenAI Universe. OpenAI Gym is just a platform to, it's kind of the Kaggle of reinforcement learning, let's say. So it's a platform on which you can put your results on a leaderboard and cooperate with other people. I think OpenAI Universe is more complicated environments for research, but I'm not really sure. I think it's similar, but without the social aspect, but I might be wrong.
It's also for
Mm-hmm.
Can you tell us the pros and cons of reinforcement learning as an MCP problem? Basically, Markov is based on the Markov. Of that state is based on the previous state, right? So, is there anything can we play with it?
You can always reformulate the problem in a way that the Markov property doesn't affect you, no? So you say, okay, if I see that the state is going to be an issue, then I declare the new state to be some summary of the previous states, and then I just forget about it. So that's not the issue. So the difference is between having a model of the world or not, assuming a model of the universe or not, rather. Yeah. So reinforcement learning means I don't necessarily need to have a description of the universe. I can still do stuff on it. I can still behave well without understanding how it is. And the Markov decision process, well, you have a structure of it. About
the model that include the way they follow the weekend.
Well, there are actor critic methods. It's a different kind of problem. So you may not need to know the value functions. So if you have the value functions, you can derive a policy. But so policy-based methods like actor critic or policy gradients, they go the other way around. So they say, okay, I don't care about the value function. I will just assume that the policy is parameterized by something and try to optimize that something accordingly to the payoff. Actor critic methods kind of combine these two. I say, okay, I will optimize the policy, but I will keep track of the value function somewhere, and I will optimize the policy trying to follow my new guess of the value function. So that's.
Are there any other alternatives around
I'm not. I don't know, to be honest.
Okay, so I'm sorry about that. I have to stop it here because there's another
Yes, sorry.
in like 20 minutes. We have to leave the premises. So thank you all for coming. And I'm just repeating again that we are transferring to a new bipod for who will share, I think. So like this, you can go ahead. Pablo is joining us, and if you don't know, just wait somewhere downstairs or here, and I will get you there. So thank you again.